Which brings us to batteries. We use chemistry to generate electricity all the time. I'm willing to bet money that most of you have at least 2 batteries in devices on your person. Your cell phone and your calculator. And you may have more. They run on batteries. Batteries run on redox reactions. So what is electricity? Electricity involves electric current. Electric current is a flow of electrical charge. It's a flow of electrons. So here's an illustration of a wire, and we have electrons moving through the wire, and that's what electricity is. Because redox reactions involve the transfer of electrons, they can be used to create electrical current. Let's look at this reaction. We looked at this one earlier. Zinc metal reacting with copper ions to form zinc ions and copper metal. If we look in the activity series, we see that zinc is más macho than copper, and so this is a spontaneous reaction. If we separate these 2 reactants and allow the electrons access to a wire that they could go through, the electrons will actually go through the wire to get from the zinc to the copper. And that flowing electron is an electrical current, and that can be used to do work. Light a light bulb, power your calculator, all kinds of stuff. So we have a couple of terms here. We talk about an electrochemical cell. This is a device that's going to either create electrical current from a spontaneous redox reaction or use electrical current to cause a non-spontaneous reaction to occur. When we're doing that with the spontaneous reaction, we call that a Voltaic cell or a galvanic cell. We're using a spontaneous redox reaction to generate electricity. We're more familiar with the term battery. A battery is just a portable Voltaic cell. So how does this work? So here's an illustration. So in this beaker on the left, we have a strip of zinc, and this is in a solution of zinc nitrate. So we have zinc metal and zinc ions present. In the other beaker, we have a strip of copper metal and a copper nitrate solution, and so we have both the metal and its ion. These strips of metal are connected by a wire that's going through a light bulb so that we can see when something happens, and the beakers are also connected by a salt bridge. So zinc metal is more active than copper, and so zinc will become oxidized, it will give up 2 electrons, and the copper will accept the 2 electrons. So the electrons can't jump across, but they can go through the wire. And so electrons from the zinc will flow through the wire, cause the light bulb to light up, and come over here to the copper, where they will go to the ions that are in solution, and we'll see copper ions being deposited on this strip of copper. Over here, the zinc metal is dissolving, and we're getting more and more zinc ions forming here. Now, if we didn't have this salt bridge, we'd have some trouble because we'd be getting more and more positive charges here and more negative charges here. And nature doesn't like to separate charges, and that would cause the reaction to stop. So this is a salt bridge. It's a tube that it contains sort of a gel-like substance that ions can move through. And so we have a flow of nitrate ions in this direction to balance the positive charges that are being created, and the potassium ions are traveling in this direction to form the to balance the negative charge. So electrons are moving from one cell to the other, and we can make them go through an electronic device and do something useful for us. These electrodes, they're called electrodes, they have names. We have oxidation occurring at the anode. The anode is negative in charge. So the zinc is being oxidized. Oxidation is loss of electrons. So the zinc is losing electrons. There's lots of electrons available here. This has a negative charge. The electrons are going to flow away from that negative charge. They're going to flow over here to the cathode, which has a positive charge on it. Cations have positive charges, anions have negative charges. Cathodes are positive, anodes are negative. So the flow of electrons is always from the anode to the cathode. Any questions? So the driving force, because all chemical reactions have to have some sort of a driving force, is the electrical voltage. That causes the electrons to flow. If we have a high electrical voltage, we have a high driving force. A low voltage is a low driving force. And thinking about a river can help us to understand this. The quantity of electrons flowing is like the amount of water that's flowing through a river. The current of the river. If the river has a strong current, there's a lot of water flowing, right? That's the way the Kings River is in the spring when they release water from the dam. Right now, it's got a very low flow. And so a low flow is a low voltage, a low current. The potential difference, or the voltage, is like the force of gravity. I mean, what causes water to flow in a river? Lakes don't flow. Why do rivers flow? Because they're going downhill, sometimes very gradually and sometimes more steeply. So here we see a river that has a shallow stream bed. It's just descending slowly, and so the water's going to flow slowly. Here we see a river that's going over a small waterfall. There's a big difference in elevation here. And so there's a lot more potential energy, and the water's going to fall more quickly. So this voltage difference, or potential difference, is analogous to how steep the riverbed is. The steeper it is, the faster the flow, the stronger the current. There are different things that affect the voltage, but it mainly depends on the relative tendencies of the reactants to undergo oxidation and reduction. So if you have two metals that are very close to each other in the oxidation series, you've got one that's just a little more macho than the other. There's not going to be a big voltage difference. If you have lithium at the top and gold ion at the very bottom, you're going to have a really big potential difference, and the flow of electricity is going to be stronger. Why do batteries wear out? Why don't they just keep generating electricity forever? That'd be awesome, wouldn't it? Well, what happens is, as the reaction continues to occur, we're forming more and more zinc ions here, and this electrode, the anode, is actually being eaten away. And over here, we've got copper ions that are plating onto the copper electrode, the cathode. Eventually, we're going to run out of copper ions. So the reaction stops for the same reason most reactions stop. You run out of reactants, and your products accumulate. And so then the reaction stops. There are several different kinds of voltaic cells. There are dry cell batteries. Didn't mean to do that. Dry cell batteries, like you probably have in your cell phone. They don't have a lot of water in them. There are lead acid storage batteries. These are the sorts of things that we use to start cars and to run boats. They're big and they're really heavy. And then there are fuel cells. Fuel cells are pretty neat. Here's a picture of a car. It's the Honda Clarity. It's a hydrogen-powered fuel cell automobile. It runs on hydrogen and oxygen, and the only emission is water. That sounds pretty awesome, doesn't it? And the problem is, where do you get the hydrogen? But this is an illustration of how that works. So you have hydrogen coming in from one side, and you have oxygen coming in from the other side. And you've got one reaction happening at the anode and the other at the cathode. So hydrogen is being oxidized at the anode, and oxygen is being reduced at the cathode. And electric current then flows through. So a hydrogen-powered car is an electric car. It's just powered by a hydrogen-oxygen fuel cell instead of a conventional battery. The product here then is water. They also use this process to fuel spaceships. And what's really nice is it makes completely pure water, and so then you also have a source of water for the astronauts to drink. Kind of neat.